For a very long time, humans have imagined what life may be like in other worlds. Thanks to the James Webb Space Telescope, the most powerful telescope in existence, that question can finally be answered. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have noticed some peculiar anomalies from one of the planets in the system, Proxima b. These anomalies, called artificial lights, have puzzled the best minds in the scientific community. But what are they? Do these lights suggest the existence of intelligent life on the planet? Join us as we explore James Webb's terrifying discovery of city lights that changes everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To carry out such an interstellar search, American astronomers Jill Tata and Thomas Pearson launched the Search for Extraterrestrial Intelligence, SETI. The project launched in 1984. The nonprofit's objective is to gather spaceborne radio signals. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains because they are less dispersed or absorbed than other types of radiation. But in the past 30 years, no verifiable alien signal has been discovered. After that, the James Webb Space Telescope's successful launch aided in the quest to examine a range of undiscovered planets orbiting far-off stars. The largest telescope in the world, floating roughly 1 million miles from Earth and outfitted with incredibly sensitive detectors, will be used. 20 years ago, there were no known planets outside those in our solar system, but since then, more than 4,000 planets, also referred to as exoplanets, have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial plant life. The Galileo spacecraft turned its equipment back toward Earth when it was en route to Jupiter and found a definite indication of the presence of plants. The instrument detected the vegetation red edge, VRE, biosignature, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth, covered in a jungle, should have a strong and easy-to-detect VRE signal. The JWST will measure the VRE of far-off Earth-like planets in the habitable zone around stars. They could be important signs of life in the exoplanet's atmosphere. When sunlight crosses a planet's star, the JWST may be able to detect it as it enters its atmosphere. The light's missing wavelengths would then be discovered via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the JWST can recognize. This method may be used to determine the composition of the atmosphere and whether life is possible. It is likely that life could exist on Earth-sized planets with atmospheres similar to our own, with a predominance of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't usually present, one may be able to detect technological life. Chlorofluorocarbons, CFCs, generated for use in refrigeration and cleaning products, would probably be noticeable to aliens monitoring Earth's atmosphere from a distance. If the JWST found CFCs in planetary atmospheres, that would be a clear indication of civilization. Actually, life on exoplanets might not even remotely resemble life on Earth. Sometimes, even earthly life like extremophiles can seem alien. This is a group of organisms, primarily bacteria, that can endure environments where other living things would perish. Some humans can withstand heat up to 250 degrees Fahrenheit, while others can withstand colds as low as -4 degrees Fahrenheit. Some can survive in strong acids with pH levels below 3, while others can be found on Earth in places where we would not expect to find any life at all. But since planets like Earth are more likely to support life than planets with severe temperatures or acidic conditions, it could be a good idea to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are less common and typically have shorter lives in our universe. The likelihood of studying planets orbiting red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. There's more time for the formation of life and evolution to produce complex life forms because these stars have significantly longer lifespans. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of JWST's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone might have liquid water on their surfaces. The TRAPPIST-1 star, despite having a much smaller and colder mass than our Sun, radiates light similar to that of Earth due to the close orbit of its planets. The best chance for humans to see city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun and our nearest star. Proxima is about 600 times fainter than the Sun, so a planet must be 20 times closer to it than Earth is to the Sun in order for it to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, in a Goldilocks-like habitable zone, where the light intensity is just right to melt water. Proxima b circles Proxima. Proxima Centauri b is an intriguing planet, though it's possible that it is airless and lifeless due to its close orbit around the red dwarf star Proxima Centauri, at a distance of only 4.6 million miles. For comparison, the distance between the Sun and Earth is 93 million kilometers. Proxima b's close orbit exposes it to strong solar winds that could destroy its atmosphere. However, its proximity to the star also provides enough sunlight to create temperatures and liquid water similar to those on Earth. Proxima b is thought to be tidally locked, meaning it always shows the same side to its star, much like how the Moon always shows the same side to Earth. Proxima Centauri is about 1/8 the mass of the Sun and burns far less brightly. Despite being just 5% of the Earth-Sun distance, which might suggest Proxima b would be a red-hot cinder, liquid water could still exist there if the planet has an atmosphere to retain heat. The total energy reaching it is only 65% of what Earth receives, though Proxima b is likely tidally locked, creating permanent day and night sides with significant temperature changes. The planet also receives 100 times as much high-energy radiation, including X-rays and ultraviolet light, compared to Earth due to its proximity to Proxima Centauri. Proxima b is bombarded with high-energy particles during star flare-ups, unless it has a magnetic field similar to Earth's to shield it. However, certain conditions might make it a habitable world. Sadly, models suggest that the atmosphere of tidally locked planets may collapse due to freezing volatile gases on the night side. On Earth, volcanic activity replenishes the atmosphere, and a strong magnetic field helps retain it. Since we know nothing about Proxima b's volcanic activity or magnetic field strength, it's impossible to predict whether it has an atmosphere. But an atmosphere would indicate the existence of seas, which would hint at the possibility of life. If Proxima b had a sophisticated civilization, it might have solar panels covering the day side to generate electricity for lighting and warming the night side, which would otherwise be too cold and dark for habitation. The discovery of Proxima b has sparked interest in determining if it transits its star's face from Earth's viewpoint. Such transits would allow scientists to measure the planet's size and mass, helping determine its density, which would confirm its rocky nature and provide information about the materials in its rocks. During a transit, starlight passing through the atmosphere could reveal the planet's nature. However, the chances of the orbit being aligned for scientists to observe a transit are only 1.5%. The star's tendency to flare complicates matters. Astronomer David Kipping of Columbia University explains that as a rocky planet absorbs sunlight and re-emits it as infrared light, it produces a distinct type of infrared radiation, different from stars like Proxima Centauri. The James Webb Space Telescope, JWST, was specifically designed to study infrared light, and Proxima b's infrared heat signature is key to detecting its atmosphere. The infrared portion of the spectrum has a strong affinity for the JWST, which could even detect city lights on Proxima b's night side, even if as faint as what Earth's civilization currently uses. Proxima b's day side is thought to be heavily coated with solar panels, reflecting starlight due to its unique spectral edges. As Proxima b orbits its star, day and night should be similar, with cool evening lows following daytime highs. However, the temperature difference between day and night depends on whether the planet is composed of bare rock, as an atmosphere or ocean would conduct heat. If there's no atmosphere, Proxima B's day and night sides will differ dramatically in temperature. The day side would re-emit all the energy it receives, resembling a black body, while the night side would appear as a frozen hell. If the temperature difference is less extreme, it could indicate an atmosphere. The JWST will take only 11.2 Earth days to measure the infrared radiation from Proxima B's two faces after it completes its orbit. If Proxima B has an atmosphere, the next step will be analyzing its composition. The presence of gases like oxygen, water vapor, and methane could suggest habitable conditions, if not actual life. However, capturing starlight bouncing off or passing through the planet's atmosphere is challenging. While Webb can only examine a few of the closest potentially habitable worlds, its primary limitation is tracking changes in atmospheric concentrations of methane, carbon dioxide, and water vapor. Webb cannot detect unbonded oxygen, the strongest sign of life, though mixtures of these gases may still suggest life. One planned observatory, the extremely large telescope, scheduled for operation in the mid-2020s, will be able to conduct a detailed atmospheric investigation. Ozone is among the substances that the JWST could detect, providing critical clues about habitability. Until these ground-based telescopes are operational, the JWST will provide valuable data for a decade or more. In the future, more powerful space telescopes could use advanced techniques to block a star's blinding brilliance and reveal starlight reflected from the planet. Similar to covering a light with your hand to see distant objects, future space telescopes could employ small internal masks or large external umbrella-shaped satellites to block starlight, making it easier to study reflected light. Unfortunately, many gases produced by life on Earth can also arise from non-biological factors. For example, methane is released by both cows and volcanoes. Sunlight can also create oxygen by splitting water molecules through photosynthesis. As astronomers search for alien life, they are likely to encounter false positives. A thorough understanding of a planet's geological and atmospheric processes is needed to differentiate between biosignatures and non-biological factors. The next wave of exoplanet research could provide compelling evidence for the existence of life beyond Earth. The preliminary data from the James Webb Space Telescope offers a glimpse of significant advancements to come. Whether life exists elsewhere in the cosmos remains one of science's most pressing questions. Life may be abundant across the universe, or we may be completely alone, isolated on a solitary planet in the vastness of space. In either case, the answer could lead to significant philosophical and psychological shifts in humanity. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.